Let's now build a for loop abstraction that collects results. What it means is that we will be able to loop over an instruction, which is a loop body, and collect results and create an output list, which is the set of results that we collect. So in order to implement this, we will use state, a cell, and higher order programming together. And that's very interesting because we're using an imperative concept together with a functional technique in state and higher order programming. And there's no antagonism here. They work together very well, and using cells can give extra power to these data flow programs. So our new abstraction, in fact, generalizes the existing declarative for loop of Oz, and it's called a list comprehension. So just to explain, to start the definition of for collect, we start by showing the declarative for loop in Oz. So here, for example, for I in 1, 2, 3, do browse I times I end. This will execute the three statements in order, which is the loop body, but with different values for I. And this is done by making I reference the elements of the list successively. So we have these three statements executed one after the other. And notice that the iterations are independent. The identifier I is independent in each iteration. In each iteration, it references one element of the list. Now, this declarative for loop has the problem that the iterations are independent. So it cannot combine the results of these iterations. So we would like to be able to do this. We would like to collect or accumulate the results obtained in different iterations together in one output list. So, for example, we would like to do something like this. For I in 1, 2, 3, we would like to accumulate I times I. So create an output list which contains this I times I, so 1 times 1, 2 times 2, 3 times 3, 1, 4, 9. So the existing for loop cannot do this, but we will define a new abstraction, for collect, that can do it. And the for collect abstraction, therefore, extends the for loop with the ability to accumulate results. And here's how it's called. So R, the output list, is equal to for collect. Here we have our input list 1, 2, 3, and here we have a procedure which is used to turn our loop body into a value in the language. So this is an example of higher order programming. So this statement here is the loop body, and the two arguments of the procedure I and C are the two identifiers that we will need in the loop body. First of all, the loop index, I, as usual, and second of all, a new thing, C. C is the collect procedure. So for collect actually creates this procedure, and it's usable in the loop body. So if I call CX in the loop body, I will accumulate X in the output list. So if I call, for example, R equal for collect 1, 2, 3, and with the procedure I call CI times I, this will create the output list 1, 4, 9, because it's going to call C 3 times with I is 1, with I is 2, and with I is 3. And this will create our output list. So that's the idea of the for collect abstraction. Now, how do we implement it? Well, the tricky part is implementing the collect procedure. How do we implement this collect procedure? Note that C cannot be written in the functional paradigm. In the functional paradigm, calling C several times with the same argument, for example, would do exactly the same thing. But this is not what's happening here. Here it has memory. Each time we call CX, we need to append X to the output list. Something new is created. Things change on each call. That means that C can only be defined using state, that is a cell. So we need to use a cell to append X to the output list. But note, seen from the outside, for_collect is still functional. So we're not leaving the functional paradigm from the outside, even though we need a cell to implement for_collect. So how do we do it? Well, let me show you with an example. Assume that we're building an output list and we've already added 3 elements. So R is the output list. We've added elements 1, 4, 9, and we're not done yet, so we have some unbound tail here, R1. If we want to add the next element to the output list, we need to bind R1 to the next element. Let's say it's 16, followed by a new unbound tail. If we do this binding here, we in fact will update R, and R will be 1, 4, 9, 16, R2. And the new end of the list then is R2. So what does this tell us? Well, we start with R1, which is the end of the list we're constructing, the unbound variable at the end. We bind it, and we come up with a new unbound variable at the end. So in fact, the cell that we need will have to store the end of the list. It starts out by storing R1, and at the end of the operation where it adds 16 to the end of the list, the cell will store R2. So this looks as follows. We have here a cell. Let's call it ACK for accumulator. Initially, its content is the end of the list. And here's our collect procedure now. Our collect procedure, which will do what we just saw on the previous slide. So it will take the end of the list, which is the content of ACK, and bind it to X bar R2. So this will add X to the list, and the new end of the list is then R2. So it has to replace the content, the old content of the cell, by a new content, R2, because the cell always has to contain the end of the list. So these two cell operations will together have the effect of adding X to the output list, appending X to the output list. So this gives us the following definition of for_collect. So this procedure for_collect, it has 3 arguments. So the input list, the procedure which represents the body of the for loop, and an output list. So we first create the cell ACK. Note the value is YS, the output list, which starts out being empty. And then here's our collect procedure, as we saw it in the slide before. So it binds the end of the output list, and then it replaces the content by a new content. So if we do this, then it's enough to do a simple iteration here, X and XS, and call P with the collect procedure and the value of X for each element that we're iterating over. And at the very, very end, when we're done iterating over all the elements of XS, we have to bind the end of the list to nil. So the content of ACK, which is the end of the list, has to be bound to nil. Note, important, we do not want to do ACK : equals nil. That would replace the content of the cell, but we do not want to do that. You see why? We want to bind the end of the list and not replace the content of a cell. Okay? There is a final point here. We need to write for_collect as a procedure, even though we will call it as a function. It's because we need to access the output YS. Even though we call for_collect as a function, defining it as a procedure gives us access to YS because we need to use YS in the body of for_collect. Notice we have defined for_collect on lists, but in fact it can do more. It also works on streams like any list function. Running for_collect in its own thread makes a concurrent agent. So here's an example. I have an input stream XS, an output stream YS, and if X is even, X mod 2 is 0, then I accumulate X times X. So this is an agent that reads an input stream, and returns an output stream that contains the squares of the even elements of XS. So our for-collect list comprehension also lets us build concurrent agents in a very compact way. And there's a final point here. Notice that for-collect is an abstraction that combines and generalizes both map and filter, called a list comprehension. Some languages have syntax for this. For example, Haskell and Python directly support list comprehensions. And the point is that in Oz, list comprehensions give you something more. They can also be concurrent agents in the deterministic data flow paradigm. And another point is that for-collect is defined by combining cells and hardware programming. There is no antagonism between these two paradigms. They can be used together to the benefit of both. Because even though for-collect uses a cell internally, it is completely deterministic when viewed from the outside. This is because the cell is used in a single thread in a well-defined way. And there's an alternative definition. Note that if we might call the collect procedure in more than one thread, it might be the case in the function body that we do that, then we need its changed definition. Instead of using : equal and access, so instead of using : equal and access, we will use exchange instead, because exchange does both operations, accessing the old content and updating the new content atomically. That means as one indivisible operation. This will avoid errors if the cell is used by multiple threads. So the final definition of for-collect, in fact, will use exchange, because this allows the collect procedure to be called in multiple threads.